part of the idea today is I hope that I can share with you some of my ideas about what I'm doing, but also I'm looking forward to learning about the work going on here and to learn new things, and that's what it's all about. So let me begin. Recently, there's been a lot of interest in driven condensed matter systems. And this is in part due to tremendous developments in ultra-fast optics, but it's also due to many interesting proposals of exotic non-equilibrium states. So today, I'd like to tell you our ideas about this. The key question that motivates the field is, can we have light-induced phenomena that's inaccessible in equilibrium? And here the idea is, hello, welcome. Here the idea is that when you shine terahertz radiation on a material, you modify its effective potential, but also you can tune its coupling constants. And so these type of experiments have led to all kinds of interesting types of light-induced phase transitions. Now, examples might be that you might actually access states that are metastable in equilibrium. Also, you might induce order parameter fluctuations. Hi, Vadim. Thank you for coming.
Thanks for coming.
But here, the idea is that the states that you get are often intimately connected with those that are there in equilibrium. Okay? They might be metastable states, they might be states. And our merry gang, Daniel, who's a guest researcher here, Pavel, Ahana, Zekun, and I wanted more. We asked, can we get tunable light-induced phenomena that are inaccessible in equilibrium? And today, I hope to tell you about a general mechanism that we've identified for driven tunable spatiotemporal orderings that are incommensurate with a wave vector that's going to be determined by the dispersion and that oscillate in time at half the drive frequency. But before I tell you about our ideas, let me put this in some context. Let's talk about the conventional scenario for light-induced phase transitions. So in the conventional scenario, this is a many-body generalization of what happens with optical tweezers. In optical tweezers, shine light, and you modify the potential with an amount that's proportional to the intensity, to the fluence, as they call it, to the electric field squared. And this proportionality constant is the polarizability of the atom. Now, in the many-body version of this, what we have is that the light effectively modifies the potential of the system. If we have a system that is near its instability, it's near critical, then one can represent it in this way. P is our soft mode, omega P is the associated frequency, and chi is the coupling to the intensity. And you see that with increased electric field, we can shift that frequency such that it vanishes. We can get a symmetry broken phase. Okay? And we'll have a symmetry broken phase where the order parameter will be proportional to the electric field. And in particular, we're going to consider cases where we have a harmonic drive with large omega is our drive frequency. And typically, this chi is enhanced when we resonantly drive. And when I say we, luckily I'm not doing the experiments, but I believe in science as a collective exercise. And so that's why I say we. So when we resonantly drive an intermediate high frequency optical phonon, and it's anharmonically coupled with a soft mode. And as a result of that, we have this chi e squared here. And that's what then leads to phase transitions as a function of fluence. Did you have a question, Buddy?
Yeah. When you say resonantly, this is just a proxy for strongly?
Resonantly
or
means
there some kind of
well, it's resonantly, which means that we're exactly at the frequency.
Why is that necessary?
Well, we'll see later on. It gives us the maximum, and it gives us the maximum term for this. Okay. And you'll also see you want the maximum term. Okay, so you get that's a maximum amplitude, and therefore we have the maximum cost, because this is basically Q squared P squared here. You see? And if I drive it resonantly, Q will be proportional to E.
I understand, but as a theorist, the only thing that matters is chi times E squared.
Yes.
So I can just crank up E.
Okay, but what we'll see later on why we want to be on resonance, but you end up getting the optimal conditions. But in fact, as you correctly point out, we can be off resonance, but we'll see that the conditions are not optimal. Okay, and the other reason, of course, for resonantly driving this mode rather than that mode is it gets around heating issues. Okay.
But, I'm sorry, may I ask?
Yes.
To that point.
Yes.
Here you've cast the problem in terms of changes to a static envelope.
Yes.
But in fact, if I have an E of t, my real Hamiltonian is time dependent.
Absolutely.
And so that will do two things. Number one, in addition to changing the Hamiltonian, if you like, it will change the distribution function.
That's
by
true.
Making excitations. And second, just in principle, there are parameters in the Hamiltonian that are time dependent.
Absolutely.
So what difference does that make?
Well, in this case, we're considering insulators. So we have a gap, but this, first of all, I'm only providing the context now. I'm not actually, we're doing something different than this. But of course, in order, and Angel Rubio, who's here, I believe, or who comes here quite often, he's been very involved in looking at details of that. Here, I'm just trying to give you a flavor for what happens here. And what's important here is that material is close to an instability. Okay, then the light drives it into an instability that would have occurred as a function of temperature, but is occurring at a temperature where it would naturally occur. Okay, but the details we're not going to get involved with. I just wanted to give a flavor. Okay, is that okay? And we can discuss more later. Okay, and so for example, one example of this is in a ferroelectric. Okay, you can take a paraelectric for so this is a system, for those of you who aren't familiar with ferroelectrics, this is a system that breaks inversion symmetry into a polar group. You can go at some temperature where you have a symmetric state, then you can turn on the field, you can get a double well, you can break symmetry, and this has been seen in a number of ferroelectrics. I should say that in this general area, these are two excellent reviews, one by Angel Rubio, who I'm hoping to meet when I'm here. And what has been seen are light-induced charge density waves, magnetic systems, and even, though controversial, light-induced superconductivity. So lots and lots of different things. Okay. Now, in parallel to all of this, well, before we talk about parallel, let's say, in order for this to work, the material has to be close to an instability in equilibrium. The nature of the ordering is determined by soft modes in the equilibrium system. And the characteristic features are generally not tunable. That is, the transient order is usually commensurate with the underlying lattice, okay? And I say usually because of course, but usually. Okay. Now, let's talk about a parallel quest. A parallel quest in the community is for tunable incommensurate lattices. And incommensurate, of course, means that we have a misalignment of two or more periodic structures. Okay. And a standard model for this is a flavor of the Frankel-Kontarova model. The Frankel-Kontarova model, you have masses connected by harmonic springs with a particular equilibrium distance. And they are subject to a potential, a harmonic potential, as shown here, whose periodicity is different than that of the springs. And this simple model has been used, it's very rich, and it's been used to study charge density waves, flux lattices, and some form of long Josephson junctions. So one of the things that experimentalists do is they actually make heterostructures, with different periodicities, trying to get some incommensurate structure. Because of course, when you have competition between different length scales, that's often when you get exotic phases. All right, well, most recently, of course, there's been a lot of excitement about twisted moire materials. Nicolas, this is for you. Twisted moire materials. And there, the idea is not only do you stack, but you put a twist in. And the twist has profound effects on the band structure. And in fact, as we've learned, and again, I say we as a scientific community, you can go from metal to insulator, you can introduce topological terms with band folding, all kinds of interesting stuff. And what are the motivating questions there? Motivating questions are, how do the properties of the system change as the incommensurability varies? And can we engineer incommensurate structures with desired functionalities in quantum materials? Now, in these twisted moire systems, what happens is, of course, at various twist angles, you get flat bands, you get strong correlations, you get exotic quantum properties. As far as I understand from my experimental colleagues, once you get to a certain twist angle, you're stuck. You can't move it to something else. It's not reversible. And so one of the questions is, can we come up with reversible, switchable incommensurate structures? So our motivating question is, can we generate light-induced tunable ordering at finite momentum? Now, I taught E&M, a graduate E&M last term, and you might just say, wait a minute, this doesn't make any sense, your question. Why does it not make any sense? Because light is basically Q going to zero. So how do I transfer momentum to a solid? Well, you can do it with nonlinearity, but you say, wait a minute, nonlinearity, that coupling is tiny, but I can enhance it by parametric resonance. And so that's the game we're going to play. So let me tell you about an alternative pathway to light-induced phases that our Mary gang has thought about. Okay? And what I'll do right now is I'll give you a conceptual overview, and then we'll go into the nitty-gritty. So the key thing is that we have to be in a symmetry-broken state. Okay? Remember that before we were sitting close to an instability. Now we're in a symmetry-broken state. And the key ingredients are nonlinearity, parametric resonance, and spatial dispersion. So let's unpack that. How does that work? Well, parametric resonance. Parametric resonance, of course, means you put energy in, amplitude goes up. The classic example is a pendulum with a pivot that moves. An example that we all learn of as children is on the playground. We're on a swing, and we realize that if we pump at a certain frequency, our amplitude is very large. Now, as physicists, we know that what that means is if we drive at twice the normal frequency of the swing, then we'll get parametric resonance. Now, how does that work with a solid? In a solid, You can think of a solid as lots of little pendula. Okay, so suppose we drive it at some frequency. Well, it's very unlikely that at q equals 0, we're going to get a mode at omega over 2. However, the atom has something that the kid on the swing does not. It has momentum. It has dispersion. So conceptually, what we're suggesting is the following. What we're suggesting is that we drive at some large omega this frequency, omega q. So Vadim, this means that our big frequency is exactly omega q, because we're resonant, okay? Because we're symmetry broken, we can couple, we can have a q p squared term, and we'll get parametric resonance at omega over 2. Now there's nothing there most of the time. However, because we have a dispersion, we can connect to minus q and plus q. So we have a combination of nonlinearity, parametric resonance, and spatial dispersion. Okay. So once again, because we're in a symmetry broken phase, this is different than the, we can couple, we drive this, we have parametric resonance, and then we'll find that we will have spatiotemporal ordering with omega over 2 and q0.
Wait, I'm sorry, why is it broken symmetry phase of that going?
Because we need to have a qp squared. Q breaks inversion symmetry.
We have materials that don't have a broken symmetry that don't have inversion.
Well, first of all, we don't have to. We can actually get, I should tell you, as you'll see, we can have systems that, I'm going to show the terms. This is the easiest case. That's the main.
But it's basically just you need the matrix element to be non-zero.
That's correct. That's correct.
That's all I want.
And so the point is, I can also get this if, for example, I have spins, if this is a spin mode and I have a dynamically induced Dolinsky-Maria interaction, as I'll show you shortly. So I need this to be non-zero, okay? That's the main story. And I would like gamma to be as large as possible, because as we'll see, the threshold, this occurs at a threshold field, because I need to have this as primary decay channel. And it turns out, as we'll see when we do look at the numerics, the threshold field will be inversely proportional to gamma. So we're doing the simplest case right now, but it's what we need is a matrix element. Okay, thank you for the clarification. Are there any other questions? The only questions are coming from the front row. Okay, well, please ask questions. Okay. Okay, so let me just give you a schematic of how this works. The schematic is that we pump our system. Let's say we resonantly pump our Q mode. It's anharmonically coupled to this P mode. And one of the recent developments that's very exciting that Andrea Cavallari has been working on, and I'm excited that he's coming here next month, is time-resolved X-ray diffraction. I find this amazing. They can do X-ray diffraction on timescales less than the pulse width. That's 10 to the minus 12 seconds. So what would we expect in that? Well, we get a Bragg peak, but now we would get a peak, well, for below the threshold, and the threshold is determined by the widths of those P and Q modes. Below the threshold, we get nothing here. But above the threshold, we'll get an amplitude that varies with time as 2 over omega. Okay. Now, in a similar way, it turns out, but the effect will be less pronounced. You can also do this in magnetic materials with large spin orbit coupling. Then you can have a dynamically induced Dolinsky-Maria interaction, and you would expect something similar. But the experimentalists prefer the polar materials because we have the best chance of seeing it within their parameter regimes. So that's why we focused on that.
I'm confused.
Yes.
Do I understand parametric pumping? Because when the end result, the modes at plus minus Q naught, the new expectation value is bilinear. It's a dagger or something.
Okay, this is all classical, of course.
Right.
Yeah.
No, but the question is that if, since you mentioned X-rays, I started imagining how would X-rays scatter off of that, and usually X-rays scatter off mean displacement.
Yeah, but here I'm going to show you what it looks like.
Okay,
It's basically
fine.
a standing wave. I'm basically going to have a standing wave that's also at Q0 that's oscillating at omega over 2. But let me show you some pictures. This is just to give you the conceptual overview, but hopefully I can answer your question.
Sort of coherent Raman together.
Pardon? Yeah. Okay. All right. So let's consider a polar system because that tends to be the system that's easiest. And we considered lead titanate because lead titanate, Alaska Zubedi in Paris had done some numerical work that we could tap into. So let's take lead titanate. It can be anything you want, and we drive it harmonically. Now, let's look at the action. This is just a classical action. And let's take it apart. So let's look at the standard terms. Here we have a time-dependent term. Here we have a gradient term. Here we have our quadratic term. And these are the self-interacting nonlinear terms. And note that because we're in the symmetry broken state, we have this p cubed. Okay. Now, of course, we have exactly the same thing for P and Q. Okay. Now let's get to the interesting part. What is this? Well, we have these terms. Okay. This can be absorbed into this, so we're not too worried about it. Now we want the leading cubic terms. So we have this term. This term will be higher frequency because it's Q squared. And we have that term. Now, this will only be finite in a polar material, okay? If we look at a spin system, we look at this term, okay? But for the moment, we're going to consider a symmetry group where this is constant and this is 0, okay? And we're doing this because we really want to make our gamma as large as possible. Okay, so now what are our classical equations of motion? So classical equations of motion for Q, everything is as usual, but now we have a minus gamma p squared term that came from our p squared Q term. And here for our P, we have a P double dot, then we have this term. I should say that we're including isotropic dissipation here. This minus 2 gamma PQ comes from our PQ P squared term. This is our nonlinear part, and this is our Langevin term. Okay, so we treat dissipation isotropically, and we put in temperature using Langevin. So let's look at what happens to P and Q. So the first thing we did was we did numerics. And for simplicity, we're going to consider fields that are supported by one space and one time. We can easily generalize it to higher dimensions, but for the moment, let's just do this because it's simpler. So let's look at a numerical solution at t equals 0. Okay. And for the moment, we're going to start simply. We're not going to consider the nonlinear terms. Right? So that means we're not considering the PQ P4 term. Okay. So what happens? We're taking our initial conditions so that P and Q are small. They're chosen from a small distribution. And what we find is, so this is X, and this is space, this is time. What we find is below a threshold field, we get exponential decay in P. Okay, and you can show that this exponential decay goes like 1 over beta. It's not that surprising. Okay.
I'm sorry, can you go back to your equations for a second?
Sure. Sorry. Yes.
So we're linearizing this, and
we're not linearizing it. We're doing it numerically.
oh, but I thought you said you were. I'm sorry, and then I made a mistake. So we're.
No, I'm not considering these terms.
The VNLs.
Yes.
The 2 gamma PQ is.
Yes. Yeah.
Sorry. Okay. So that was.
So all I'm doing is I'm not considering these terms. Well, actually, numerically, they have to be very small just for stability, but they're really tiny.
Okay, but anyway, now I understand the equation. The 0 temperature means we're setting eta equals 0.
That's right. And in principle, we do put in a beta, so in principle, you can say it's 10 to the minus 15 or something.
But wait. I thought you said that, and now where is the drive? Oh, it's in the Q equation.
The Q equation is here.
At this level, a totally linear equation.
That's right.
I can just replace the Q by a function of the drive, so what I get is P times some drive thing.
Exactly. And that's why we're resonant. So this is some E over some denominator, right? So that's why it's resonant. And actually I can solve it for non-resonant, but it gets a little more complicated.
And
yes,
beta is effectively 0 in this, or effectively?
I'm actually taking beta to be finite. It's isotropic damping. That's why. Okay.
Right. So that means that you have basically for weak fields you have an overdamp. You have an overdamp system. So for weak fields, at least, the thing just decays.
That's exactly right. Okay. Does that make sense? Thank you. Any other questions?
Sorry, what do you mean decay? It settles into a linear response.
Well, what I'm saying is we're going to look at I think Andy's referring to this.
Yeah, but and this was an impulse or a steady state?
It's a steady state. We're doing
so that means that there should be a steady state with a non-zero amplitude at all space and time because it's linearized.
No, but I'm just sending in a harmonic cosine. So all this is saying is I get something. It's decaying. P is decaying.
Oh, is it time average P or
time average.
Frequency?
So what's plotted is not P, but time average, the zero frequency component of P. Okay.
Absolutely. Thank you. Thank you for your question. Did you have another question? You were holding on to the microphone. Okay, you were just in ready position? Okay, all right. Now, even with this, if we look at the log of the spectral density, we can get some information. So you see this is on a logarithmic scale. These lines are remnants of the initial conditions, but you see that they're very weak. And this is our dispersion. Okay. All right, now what happens above some critical E? Above some critical E, you see that we have a density wave in space and in time. And if we look at the log of the spectral function, we see that at omega over 2, which is just here, we have a whopping response. And this is going to be our Q0 here. Andy, you're frowning. Is something wrong?
I'm just confused.
This is our parametric.
That there's a response at a very definite Q.
And this is
what's the
so the drive is
But how do I see there's an exciting response at that particular frequency? It looks to me just like a green vertical line.
Well, those are the harmonics, but I think the main thing is that this is the largest. If you look, this is yellow.
Oh, I see. That's hard for my eyes to see. Okay, now I understand what you're saying. So if I were to plot a vertical line cut, there would be a linear scale. There would be a big peak at omega equals.
Absolutely. So what we do then is we can average, and we can ask how does P, our density wave, what does the onset look like? Well, it looks like a square root. It's dangerous to say it's a phase transition, but it certainly has an onset. And if we look at the late time Fourier transform, we see that for E less than EC, this is just flat, but just confirming this, we see that there's plus Q0 and minus Q0. Yes.
So point 2 is determined by the
dispersion. By the dispersion. Yes, there's an exact resonance condition. So the idea is that we're at omega over 2. If at omega over 2, which is here, I have some Q0. Omega over 2 here, there's nothing. The drive in this is 1 because it's omega over. So here I have nothing. But I go across here and I have Q0. So what I have there is a standing wave of plus Q0 and minus Q0.
So I guess the thing that's not adding up. So I'm thinking that beta is effectively 0, so that the sharpness of that onset is controlled by how small beta is.
Well, beta is finite. Beta
Is this threshold determined by beta?
we're going to show, I'm going to show you where it comes from. Okay. So, all right. Well, yes.
Is this a known, I mean, this is a classical nonlinear differential
Yes.
equation.
Yes.
Is this a known equation that has some Russian person's name attached to it and its behavior has been classified, or?
Well, I don't know. We talked, I mean, of course, parametric resonance has been studied a lot. And we talked to a number of Russians, including your colleague, of course, Oscillate and others, to delve into the Russian literature. I mean, the standard question, which is, I guess, Andy's too polite to say it, is why hasn't this been done before? And as far as I can tell, parametric resonance, of course, is a very old area, and you can read wonderful things about it in the Russian literature, in Arnold and Lender and Lifshitz. However, what I think is new here is we've combined parametric resonance with nonlinear phononics, and I'm not sure if they had the reason to do that in those days.
Sorry, I never do this. I think it's distracting from the science, but I think the oldest reference I'm aware of precisely this context is a very short paper by either Shlomo Alexander or some collaborators of Shlomo Alexander, where they considered a parametric generation of magnons this way. Down conversion kind of.
Down conversion. Okay, but let me say something.
Is it not the same? It's
not quite the same. I mean, first of all, I'd be happy to see the paper. Let me also, in the cold atom community, we heard from our Russian friends in the cold atom community, they consider magnons. We are actually saved by being classical. Why? Because in the magnon community, they include nonlinearity, okay? But remember that magnons can condense at finite Q without nonlinearity. But with nonlinearity, they unbind. And so they have to go to the bottom of the band. So in some sense, the magnon case is this case, where they go to the bottom of the band. And that's also been seen in cold atoms, because a number of people pointed out cold atoms, and that's exactly the same thing. But what's interesting here is because we're classical, and because our our gamma, which connects p squared q, is larger than our alpha, which is the p cubed term, we actually, if you will, we're like having a coherent state, and we have a well-defined momentum, even with nonlinearity. So I think that's the difference. So in a funny way, we're saved by being classical. Does that make sense?
I don't know about the
yeah, but I'm happy.
Shlomo's paper or whoever's paper was line kind of.
Sure, but I think the point is that it's difficult then to get. It tends to be at the bottom of the magnon band, and we can.
My real question in asking this was, we know in classical nonlinear dynamics that there are instabilities that lead to bifurcations, period doubling, this and that, characterized by the Lyapunov exponents. So how does what you're talking about fit into that general schema?
Well, we're learning. Okay, we're learning. For example, one of the questions that one could ask is, what kind of dynamical transition is this? We don't know at this point. We're still learning. Okay, but yeah.
Just to record, what is known, what I think is commonplace, is that if you have this parametric setup, and if there's a mismatch between the driver, basically the frequency at which you're trying to swing the pendulum, and the actual frequency of the pendulum, that detuning gives you the minimal threshold.
Yes.
And at this kind of like leading order level, it's a sharp transition. Transition.
It'll be.
I kept asking what controls that.
Yeah, but I think we're going to see that when we do the phenomenology. Okay. So now we can include the nonlinearities, the higher order terms. This is the alpha p cubed and whatever something p fourth term, and ask what happens. And what we find is that we get dynamical generation of. We have our resonance. But you see, we have this little guy here. And so we have the dynamical generation of a static mode. And in particular, that static mode, it's not as strong, and it scales basically like E, because this scales, it scales like, so it scales like P squared. Okay? Now, with all of this, as Andy was saying, these are coupled nonlinear oscillators. We should be able to make some headway analytically, okay? So that's what the numeric said. So let me tell you what we did analytically. We said, let's make an ansatz. Let's assume that we're driving it resonantly. And let's see if we can get our nonlinear parametric resonance. From the numerics, the clues that we're taking is that we have this ansatz, and these are the solutions. We get two modes, okay? And if we look at the equations of motion, well, we're on resonance. And the parametric condition is expressed by, it can be embodied by this expression where this is equal to 0. This is basically telling you that you're at the place where omega as a function of E is equal to little omega as a function of E is equal to the drive frequency over 2. So if we plug these into our equations, let's look at what we get. Remember that we're resonant, so this is pure imaginary, okay? So this is pure imaginary. So here we have real, real, and this tells us, well, we expect that this is going to be real, okay? And in fact, that's verified because when we look at the structure of this equation and its complex conjugate, we actually find that P has to be real. Now look, if P is real, this is imaginary, this is imaginary, this cannot be imaginary. That means this has to be 0. So that tells us that by taking this ansatz and putting in these modes, we can get the parametric resonance. So let's see. So now this is pure real. We have a phase, and this phase is set by initial conditions, okay? And so we're going to make our life easy, we're going to set that phase in an initial condition where we know how to do a calculation, okay? So now what do we get? Well, this is 0. Therefore, we have our Q0, okay? And what we get when we plug it into the equations, and this is the answer to your question, Vadim, is that we get our E0 is greater, it's going to be related to the decay squared, the drive squared over gamma. Now you see why I want a large gamma, because a large gamma means this is smaller, okay? And this is what this P goes as square root of 0, okay? All right, so that's the threshold fluence. Okay, it's going to be related to the drive frequency, to the dissipation, and to gamma. And here I've taken the dissipation for the Q and the P mode to be the same, but if you don't, then it's just square root of BP, beta P, beta Q. Okay. So if you can see that it fits quite well the numerical experiment. In fact, you can fit it better if you increase the integration time, okay? All right, now you might say, well, we have a symmetry breaking phase. Where's the soft mode? Because that's what we were all taught. Well, the mode originates from this term. And if we go into a rotating reference frame, we can look at a static action. We're in the rotating reference frame, and we have a condition for mode softening. All right. Now, what about the leading nonlinear interaction term? Well, now that we have our standing wave at wave vector Q and at oscillating in time, omega over 2, what we can do is we can generate through these higher nonlinearities a static mode. And in fact, you can plug these into the equations. You have a dynamically generated static mode. And in fact, what you find is that this will crop up like that. And we get something that fits very nicely with the numerics. So this is just phenomenology. Now the big question is, what happens at finite temperature? Now we were all brought up with Hohenberg-Merman-Wagner theorem, which says that we have a one-dimensional system. And as soon as you turn on temperature, the phase fluctuations destroy the long-range order. So we sort of held our breath because everything we did so far was at 0 temperature. Of course, this was a driven system. Okay, Now, what happens? It turns out, surprising enough, at least to us, that the order is only suppressed when T is of order the mode bandwidth. Okay, so when the mode is saturated, so for example, here we're at the bottom of the band, okay, and you see that we have T, and this is still basically around. It's only when we go to much higher T that we actually start getting blurs. Okay, and in fact, if you look at the phase, there's a phase that's set by initial conditions. According to Hohenberg, Merman, Wagner, that phase should drift the temperature. But what we're finding is that at low temperatures, it doesn't drift, then it starts to drift, but this is the amount it has to drift to truly change the long range order. And here we see a long time Fourier transform, we see that our density wave that has components at minus Q and plus Q is well defined. The peaks here are getting smaller, but it's incredibly robust. Now, sure.
I mean, technically, you have now nonlinear equations with a noise term with some statistics.
Yes.
So what's actually done to get a solution?
So Daniel turns it into first order. Well, he can tell you that better than I can, but he turns it into first order equations and then uses methods that are known for Langevin dynamics.
I mean, I guess the question is, are you really converted to a Fokker-Planck equation and solve for a time-dependent distribution, or do you really more or less step forward in time, picking random things at each time?
I think he steps forward in time. I mean, I can ask him directly, but I believe that's the case.
Fokker-Planck would give smooth curves. Right?
Yeah, that's actually why I say that.
Right.
So I think we're just moving in time. He has initial conditions and he's moving in time and he's solving them in time.
You referred to Hohenberg, Merman, Wagner, but what is the symmetry that is broken in this state?
Translational symmetry?
Discrete or continuous?
Well, translation.
No, but I mean, because you've selected a wave vector sort of by the formulation of your problem, right?
No, it's because
it's not.
No, Q0 is fixed by the dispersion.
Yeah, exactly.
So I would say that it's broken continuous symmetry because translational symmetry is continuous, isn't it?
But then that's back to the question of phases and things. That's something at least I'd like to understand better.
Okay. Well, I guess go ahead.
Actually, no, I'll say it later. I don't know what else is coming.
Yes.
Why do you say it now?
Well, I was gonna at the very beginning when you mentioned X-rays, and I said, how do X-rays diffract from this? Because I had in mind like textbook elastic Bragg scattering.
Yeah.
And yeah, I think
It's a coherent Raman.
right. So it's much more. Basically you're scattering against a two particles.
That's right.
Fluence.
That's right. That's right.
Right, and so what? Because the way I think of Merman-Wagner theorem is that just compute the Debye-Waller factor. If the Debye-Waller factor, the thing in the exponent diverges, then you have no order. So the question here is that again, what are the soft modes? Like, how do I compute the Debye-Waller factor on this? And it seems like there are no soft modes. You're just picking this. Like, one has to think about what the soft
One has to think.
I don't think there are soft modes.
Well, that's why I showed that in the rotating reference frame, we do have a soft mode.
That's at criticality.
That's at criticality.
Right.
You're right. We don't have soft mode. So anyway, I guess to me, it was surprising. Maybe it's not to you that we had that this is robust to temperature. And we're trying to understand it. There are a couple of things that we can ask. We could say, is it because it's driven? I mean, Hohenberg, Merman, Wagner, even if you believe it's relevant, it was for equilibrium states. Okay, so I tend to think of this as because I develop a phase, and that phase that's why I think that it's a continuous phase transition. Okay, I develop a phase, and that phase should be pinned, and it's not pinned. And I should say that Daniel's done some numerics where he's taken static disorder, and this is completely robust to static disorder. However, the next thing we are doing is we put disorder that has exactly the same periodicity in space and time as our density wave, and we look to see what that does. And one of the interesting questions is, does it move it, with arbitrarily small amplitude, or does it have a threshold. So we're working on that. So the question is, do we have suppression of fluctuations due to the nonlinearities? For those of you who do biophysics, you may know about the Toner 2 model, where nonlinearities actually mean that in 2 dimensions, one can get long range order because the diverging fluctuations are cut off. It's also been suggested that we might have something that's similar to synchronization. The Premala model also has nonlinearities. Or do we just have very, very long pre-thermalization times? I should say that the time scale on which it's robust is such that for the experiments, it should be fine. But we would like to understand this better. Okay, so let's now talk about materials candidates. When we were working on this, the only materials candidate that we could find in the literature, which had been studied before, was by Alaska Subedi in Paris for lead titanate. And when we put in his numbers, they were reasonable. They were about an angstrom for Q, an inverse angstrom for Q0, and a threshold field of 3 megavolts per centimeter. Okay, and that's reasonable for these systems. We came up with a sort of design principle which suggests that in order to enhance the nonlinear coupling, the modes should come from the same atoms. And now with Jenny and Shiwei, we've been actually looking, and Daniel, of course, we've been actually doing a search for materials that might be good host platforms for what we're discussing. We're also in discussion with Andrea Cavallari about experiments. Okay. All right. So just to give you a sense of one of the materials we've looked at, this is something that Andrea Cavallari suggested. So Daniel, this is lithium niobate. He likes it because, of course, they have very pure crystals because they use it for optics. And you notice that one of the things we have to look for is at the gamma point, we basically have to look at soft modes that are half the frequency of an optical mode. So here we have these two, and he's done the calculation. This should be millivolts per centimeter. Sorry about that. And these have reasonable gammas. Of course, the experimentalists wanted different frequencies. So, we need to have a list of materials because every time they say they want something else, we have to be able to show up with something else.
But may I ask you a question?
Of course.
These are 3-dimensional materials.
Yes.
In 1 dimension, you only get 1 Q naught. In
Yes.
3 dimensions,
You get a manifold. Yes.
all
So
sort of.
you have a manifold.
How do you want me to think
So
about that?
the way, sorry, thank you for asking, and I didn't get a chance. Everything I showed you was for 1 dimension. And it can be generalized to 2 and 3 dimensions. And then you'll get a manifold where the parametric resonance condition is satisfied. And then we expect that the point group of this crystal will select certain Q zeros among that manifold. So they won't all have the lowest threshold fluence. So we're in the process, we do that actually. Okay. I just showed for illustrative purposes, 1D was easier to show. Okay, I mentioned just briefly that we don't have to have polar systems. We can have non-polar systems. For example, this term one can consider, and in particular, if we have a system that has strong mid-orbit coupling, then we could couple to an optical phonon Q, and in the continuum limit, we can get a dynamically induced Dolizinski-Maria interaction. And then we would have fluctuations of the magnetic order. Here, in fact, nickel oxide and chromium triiodide are materials that have frequencies, optical modes and magnon modes in the right ballpark for us. The experimentalists would prefer to look at the polar materials because the gammas are much bigger, but that's a possibility. Okay, so just wind up now. I've presented to you a new mechanism for driven tunable spatiotemporal ordering. We take terahertz induced nonlinear phononics, and we study parametric resonance. We have tunable spatiotemporal ordering that's determined by the dispersion of the material. And it's a direct way of generating finite momentum ordering with light. So we have continuous onset as a function of fluence, robustness to temperature, which we still don't understand, predictions for time-resolved bag, and polar materials and antiferromagnets with EMI. So the sort of picture, just to remind you, is that we pump, we resonantly drive this Q mode. It's anharmonically coupled to a P mode. And with time-resolved X-ray, we get at Q0, we get this time-dependent amplitude. And this is due to this parametric resonance. And we can also get this for magnetic materials, but we expect that the threshold field will be much larger. So, you know, of course, as always, there's a lot more work to be done. There's the characterization of the onset. I mentioned a little bit about late time dynamics. We're doing with Daniel and Shiwei and Jenny a detailed search for candidate polar and hopefully later magnetic materials. In principle, you could get terahertz generated tunable nanoscale periodic materials or even sub-nanoscale on angstrom. And you can generate local, in principle, localized magnons, maybe for computation. So with that, I will say thank you very much.
Okay, so time for questions. All right, stunned silence, I see.
Yes.
Yeah, Cyrus.
One. So about
Second row, great.
we're moving back. So for the materials realizations, is there a way to understand which materials will have a high nonlinear, large nonlinear coupling?
Well,
Some general properties, or is it just you have to do the calculation?
we think our speculation is that if the Q and the P mode involve the same atoms, then you'll have a larger gamma. And at least in the materials that have emerged from the preliminary search that we've done with Daniel and Shiwei and Jenny, lithium iodide, where the iodine bands are low and the lithium are high, seems to fit that because everything's involving the iodine. But you know, that's only one point. So at this point, what we're doing is we're looking for polar materials that are, first of all, insulators. Everything I've talked about has a gap. So one of the obvious things to do is to look at metals also. But everything has a gap, to look for insulators, to look for polar materials, and then to look for systems at the gamma point that have optical modes that are at twice the frequency of the soft mode, or the not soft mode, low-lying mode. So that's what we're doing right now. But what we think is the design principle is that they involve the same atom, but that has yet to be shown. And eventually we'll also look at spin materials, but the experimentalists are less enthusiastic about that because the response is not so good. We're also, Andrea Cavallari is also interested in doing second harmonic generation. So we're looking at, you know, materials within the light cone so that they can actually do the measurement there. They want to do some benchtop measurements before they start applying for proposals to do time resolved X-ray. So they're keeping us busy.
Other questions? Eddie?
I have a bunch of questions, just trying to think about what happens to, in the steady state, how does it stay? How does it not cope with temperature? So if you've thought about heat balance.
So first of all, the gap is crucial there. So at least according to our estimates, based on what the experimentalists tell us, the heating would be, you know, they do the experiments at room temperature. We have a gap of about an EV in this. The heating is about 40 Kelvin. So 40 Kelvin is about 4 MeV, excuse me. And so I think for systems with gaps, we're in pretty good shape. For the
Wait,
heating.
What
the
does that
question
mean?
is the phonons. Of course, the electrons are dead. The question is, are you going to heat up a phonon system?
I see.
Oh, well, I have a very naive cartoon from single or few
Okay.
particle parametric resonance. There's an exponential instability.
Yes.
It runs away. In order to get a steady state, you have to have dissipation, dispersion, anything with a T to
Yeah.
diffusion.
We have dissipate. We do have
Right.
a beta, right?
So that's the way it is.
And we also have the nonlinearity. Yes. Yeah. And in fact, that's why I said the nonlinearity has to be very small, because it's negligible, but if we don't put it in, the equations just blow up.
So that's how it goes, basically. The pump puts the heat in and it goes through out to the
Yes.
damping.
Absolutely.
It
Absolutely.
doesn't actually excite the full band of.
Absolutely. Absolutely. And that threshold is where that's the primary decay channel.
But the beta is somehow a phonon, two phonon term or
Yeah,
something.
we've dumped everything into the beta.
The beta is a gamma, P dot or something.
Yes, it's friction, but it
But
includes.
physically speaking,
It's from,
it's
that's completely correct. Yeah, we put everything in that term. I mean, this is all phenomenological.
yeah, yeah.
And we've assumed isotropic dissipation, the whole bit. Okay, well, I look forward to talking to all of you about this and other things.
All right, well, so before we thank Premala, let me just ask one other quick question. So at the moment you took your light to be at Q equals 0,
Yes,
and that was then that was important to your cosine because you precisely had plus and minus Q.
yes.
So what happens if I imagine that my light has a non-zero? So the plus and minus Q are not exactly balanced. I know it's small in real life, but
Yeah.
how,
Yeah, how do you do that?
I mean, I'm just saying that physically light has a non-zero wave. It may be small, you may want to neglect
But
it.
it's essentially Q.
But it's not exactly. So my theoretical question is just,
Okay.
if you're putting in a small momentum, then your plus and minus
Well,
Q are not exactly
I mean,
balanced.
well, we have essentially a standing wave.
I understand that.
And so as a result, you're going to have it's probably going to affect the stability of your standing wave. That's what I would guess. And the details I don't know. But what we're looking at is basically a standing wave of plus Q0 and minus Q0. But I don't actually, I mean, I don't know how to, well, it has a finite wavelength. You're right. So, okay.
So just a second, since I'm not doing the numbers in my head, but there were these very famous experiments by Joe Ornstein where he used laser grading to measure spin diffusion.
Yeah, transient grading measurements.
Right. So these were sort of macro scale Qs. They're still too small of a Q for you to be interested in. I remember that there were manipulations where.
But we're talking about Q of inverse angstrom.
Right.
So we're in a completely
No, but like if you're thinking of more M materials, maybe the game is to actually.
okay.
Yeah. It might be worth just thinking a little bit about what Joe actually did in this transient grading spectrum.
No, I don't know this work, so maybe you could give me the reference.
Transient grading, I'm sure will show.
Transient grading. Okay.
You look up for papers with Ornstein and Bernabig on them.
Okay.
Andre was still, well, he's still a kid, but you know, he was a kid.
Okay. So undergrad. Wow. Okay. Great. I don't know these, and maybe I can read it and we can talk about it. Sure. Thank you. That's what this is all about.